Hello everyone, thanks for attending my talk. I am Taegon from Samsung Research Data Intelligence team. Today I'm going to talk about FastFlow, accelerating deep learning model training with smart offloading of input data pipeline. This work is collaborate with my great colleague in Samsung Research. As you already know, GPUs are the most important resources for deep learning training. So over the decade, the performance of GPU have increased by more than 10 times. And we can reduce the training time by using more high-end and expensive GPU and by adding more GPUs with parallel computations. However, does this always guarantee the training speed up? To answer this question, let's take a look at the end-to-end deep learning training pipeline. First, training data are split into mini batches, and each mini batch is then loaded and pre-processed on CPU with decoding and augmentation. And the pre-processed data are then fed into the GPU to update model parameter with forward and backwards computation. In this pipeline, if the execution is sequential, then GPU must wait for the data processed by CPU, and it results in GPU idle time and GPU underutilizations. A simple solution is to pipeline CPU-GPU computation like this. However, the pipeline can still lead to GPU idle time and underutilization if the time to process data on CPU is still longer than the time to process data on GPU. Therefore, even if we use more high-end and expensive GPUs, and if there is a CPU bottleneck, then the training time cannot be reduced. We call such GPU idle time caused by CPU bottleneck as preprocessing stall or prep stall. Nowadays, there are various reasons of prep stalls. The first is because of the imbalanced computation speed between GPU and CPU. Second, due to the complex preprocessing that, such as augmentation and decoding the large size of data, the CPU easily becomes the bottleneck. Moreover, cloud vendors provide cloud resources with fixed number of CPUs per GPU. However, in our evaluation, we have observed that various workloads require diverse number of CPUs per GPU. So some of the workload require more CPUs than the allocated one in the GPU node, which results in CPU bottleneck. To address this problem, our team developed a technique that automatically offload pre-processing operations to the remote resources. Our idea is simple. If there is no CPU bottleneck and the GPUs are fully utilized during training, then we do not offload. Otherwise, we try to offload some pre-processing operations and data to the remote CPU nodes to minimize the CPU bottleneck and improve the GPU utilization. In fact, there are several existing work for offloading. First, TF Data Service, which is an extension service developed on top of TensorFlow, allow users to offload pre-processing operations to remote resources. However, the user of TF Data Service must manually decide which operators to offload and when to offload. Eshu, which is a recent work developed on top of TF Data Service, automatically decide the number of CPU nodes for offloading. However, as it fully offloads all data and all pre-processing operations to the remote resources by assuming disaggregated environment with high computation and network bandwidth, it may suffer from performance degradation when the remote resource has limited computing and limited network bandwidth. In contrast, our goal is to automatically decide when to offload, which operations to offload, and how much data offload by considering application characteristics and diverse resource environment. So we must address the challenge of automating such offloading decisions. Okay, this is an outline of this presentation. And next, I'll talk about FastFlow design. FastFlow, to address the challenge of automating decisions, we design and implement FastFlow, which is developed on top of TensorFlow. Here, I'll briefly show how FastFlow execute a training job and automate offloading decisions. First, FastFlow user write their training code using FastFlow API. Once the training code is submitted, then a training job is converted into a directed acyclic graph. Then, before the actual training, the profiler profile performance metrics for offloading. Once the metrics are gathered, then the plan optimizer make offloading decisions by traversing and modifying the DAG of a training job. So some of the pre-processing operations can be executed on CPU, on remote CPU, and the data processed by the remote CPU are sent back to the local GPU node for the remaining computations like GPU operations. Okay, next I'll briefly talk about each part in detail. As FastFlow is designed on top of TensorFlow, our goal is to minimize the modification of existing code for users to easily adopt FastFlow. Compared to the TensorFlow code, which is in the left side, FastFlow requires a few modifications, such as importing FastFlow package and inheriting FastFlow model and providing some configurations for offloading. Please note that users do not have to modify the main training logic. Okay, in the profiler, to minimize the profiling overhead, FastFlow execute a few iterations of mini-batches because the DAG of a training job is repeatedly executed per mini-batch. Here, FastFlow execute around 100 iterations, which is enough to collect performance metrics. And for profiler, in profiler, FastFlow measure metrics such as training throughput with local or remote CPU, and GPU computation throughput, and offloading overheads by traversing and modifying the DAG of a training job. Now, after gathering the metric, the plan optimizer decides 3 decisions for offloading. First, to decide when to offload, FastFlow compare the pre-processing speed on CPU and the computation speed on GPU. For instance, if the pre-processing speed on CPU is slower than the computation speed on GPU, then it means there is a CPU bottleneck, so FastFlow try to offload. Second, to decide which operations to offload, FastFlow compares several candidate pipelines for offloading by modifying the DAG and choose the one that leads to the maximum training throughput. Finally, to decide how much data to offload, FastFlow consider computing capacity and network bandwidth of a remote machine, and as well as the offloading overheads. For instance, if the remote CPU throughput is 3 times larger than the local CPU throughput for processing, then FastFlow try to offload 3 times more data to the remote node to fully utilize both local and remote CPU. Please note that FastFlow not only consider the CPU power, but also consider network bandwidth and offloading overhead when it decides how much data to offload. Okay, I'll briefly show a demo of the FastFlow. In this demo, first, I'll show how TensorFlow execute a training job first. Here, we use one machine with one V100 GPU and 7 CPU cores. So TensorFlow is executed on this local node. When TensorFlow is executed, and as you can see here, the GPU is underutilized. So the GPU utilization is less than around 10%. And the root cause of this is because the CPU is fully utilized and CPU is the bottleneck. So the 7 core CPUs are fully utilized, which means that the CPU is bottleneck and it results in GPU underutilization. Okay, so TensorFlow execute this training job like this, and it takes around 90 seconds. Now I'll evaluate FastFlow. For evaluation, we use 21 core remote node. So FastFlow tried to use this 21 core remote node. And before the actual training, FastFlow tried to measure the performance metric with profiling. So this is the profiling step. So FastFlow execute a few iterations of mini-batches for profiling. Once the metrics are gathered, then FastFlow make offloading decisions, and try to offload. So as you can see here, the remote CPUs are fully utilized during training to minimize the bottleneck in the local CPU node. So the GPU utilization is almost 90%, which means that FastFlow mitigate the CPU bottleneck in the local GPU node by offloading this data so it can fully utilize GPU utilization and speed up this training job. Okay, now I'll talk about evaluation. We evaluate FastFlow in diverse resources and workload, and we also compare FastFlow with diverse systems. Here, I'll briefly show some of the evaluation results. Compared to the TensorFlow, FastFlow improved the training speed and GPU utilization. However, actually, it seems obvious because FastFlow uses more resources than TensorFlow. However, the key point is that FastFlow automate offloading decisions and make optimal decisions based on the profiled metrics. We also compare FastFlow with TF Data Service, and when we have observed that FastFlow is still better than TF Data Service because of the optimal decisions based on the profiled metrics in diverse resources. We also evaluate how FastFlow decide which operations to offload. In this left figure, it represents 3 candidate pipelines for offloading. Among the 3 candidate pipelines, FastFlow choose the second pipeline in the right evaluation because the pipeline leads to the maximum training throughput for offloading. However, the decision may change when we change the remote node configuration. For instance, if we use remote node with low disk bandwidth, then FastFlow choose the first pipeline because it can avoid the disk operations in the remote node. So that result represents that FastFlow automatically changed the decisions based on the remote resource environment and application characteristics. We also evaluate how FastFlow decide how much data to offload. Here, we change the number of CPUs of remote node, and we also change the network bandwidth of remote node. And as you can see in the figure A, if this job is CPU-intensive operation, then FastFlow try to fully utilize the remote resources to mitigate the CPU bottleneck in the local node. However, if the remote node has limited network bandwidth and the job is data-intensive job, then FastFlow try to avoid network bottleneck by processing most of data in the local node. And this result represents that FastFlow automatically decide how much data to offload based on the application characteristics and the resource environment. We finally evaluate the profiling overhead. And as you can see, the profiling overhead is negligible and is less than 3% of total training time. And we can further reduce the overhead by caching the result and reusing them when the same job are executed. Okay, I conclude this presentation. Here, we design and implement FastFlow, which is a deep learning system automatically offload input data processing to remote CPU node based on lightweight profiling. And we show that FastFlow improves the training speed and GPU utilization compared to other systems in diverse resource environment and various workload. And we believe that FastFlow can be applied to diverse applications on various resource environment to improve GPU utilization and to reduce the training time. Okay, this is the end of the slide. Thank you for your listening.